Okay, so we're back for part 2 of this problem. And in part 2 of this problem, it's the exact same setup with one difference. And the difference is we're going to, rather than look for the place where the load can be safely lifted, imagine we were being unsafe and lifted the load all the way out at the end of the boom. And the question is, what happens to the crane as a consequence of that? Namely, what is the angular acceleration the crane experiences from lifting the load from that unsafe location? Okay, so I've simply redrawn my physical free body diagram here. We have the counterweights out on the short end, a distance of L over 4 away from the fulcrum point. We have the weight of the boom itself acting at the center of mass. Since the fulcrum point is located 3/4 of the way from one end, that means the center of mass is a distance of L over 4 away from the fulcrum point. And then the load, since it's now going to be applied all the way out at the end of the boom, is 3/4 of the distance away from the fulcrum point. So let's write down the torques for all of those one more time. So the torque from the load is equal to the force from the load times the lever arm of the load. Again, the sine of theta is 1 in this case because all the distances and the forces are perpendicular. And so in this case, the difference between what we're doing now and what we did last time is that R here is 3L over 4. So this is the mass of the load times the acceleration due to gravity times 3/4 of the overall length. Okay, again, we are going to choose that positive rotations point up out of the page by the right-hand rule. As a consequence of that, that means that positive torques also point straight up out of the page. So the load is trying to rotate the whole system in a consistent positive direction. So we'll label the load torque as being a positive torque. We can look at the weight. Once again, the weight is identical to what it was in the first case. So the torque due to the weight is the weight force times the lever arm, which is the mass of the boom, times the acceleration due to gravity, times L over 4. That also is a positive torque, just as it was in the first part of the problem. And then lastly, we have the counterweight. And so the torque from the counterweight is equal to the force from the counterweight times the lever arm. So this is the mass of the counterweight times G times L over 4. And as we said before, the counterweight is trying to rotate the system in the clockwise direction, which by the right-hand rule points into the page, and so that produces a negative torque on the system. Okay? So that's the setup, and so the question now is, what's different about this compared to part A? Well, in part A, we said that the sum of the torques, the net torque on the system, was equal to 0. But in this case, we know the system's going to accelerate because we've moved the load from the equilibrium point. And so what that means is that the sum of the torques can't equal 0. It must equal the net torque, which is equal to the to the moment of inertia times the angular acceleration that the system experiences. Okay? And so if I take my torques there, that's equal to the torque from the load plus the torque from the weight minus the torque from the counterweight. Okay, so in order to find the angular acceleration, what I actually need to know is I need to know what is that value for that moment of inertia. Now we know moments of inertia for long, thin rods rotating about their exact centers. The moment of inertia for a rod about the center is equal to 1/12 the mass of the rod times the length of the rod squared. But we're not rotating around the center, we're rotating about the fulcrum point. And so in this case, we have to use something called the parallel axis theorem. What the parallel axis theorem says is that if you know the moment of inertia around one axis, in this case, I know the moment of inertia around an axis that passes exactly through the center of the rod, I can find the moment of inertia around any parallel axis to that rotation axis by simply adding a constant term to this. And that constant term is m times d squared, where d is the distance between the two parallel axes. Okay, so in this case, I know the moment of inertia about the center of a rod, and what I want to know is what is the moment of inertia about this point right here, which is where our axis of rotation is, the place where the tower contacts the rod, which in this case is the boom of the tower. Well, I have to add the mass of the boom times the distance between those two axes squared, which I happen to know. The distance between those two axes is L over 4, the distance from the center of mass, which is for that moment of inertia, plus to the fulcrum, which is right here. So this is the moment of inertia for my boom in this problem is 1/12 ml squared plus the mass of the boom times the distance squared, which is L over 4. So this is 1/12 ml squared plus 1/16 ml squared. And if I find the common denominators between those two, what I find is that that is equal to 7/48 ml squared. So that's the moment of inertia for the boom rotating around that fulcrum point. Okay? So now I can use that right here for the moment of inertia in my torque equation. So let's go ahead and put it in there. Let me change colors of ink here so we can see what we're doing. So now the moment of inertia times alpha is going to be 7/48 mass of the boom times L squared times alpha. That's the right-hand side of the equation there. And that's going to be equal to this sum of the torques, which I have all my torques written there. So this is mass of the load times G times 3L over 4 plus the mass of the boom times G times L over 4 minus the mass of the counterweight times G times L over 4. Let me do a little bit of common algebra here. So I'm going to leave this alone on this side. And on this side, I'm going to factor out the G's, the 4's, and the L's. So this will look like G times L over 4 times the mass of the load times 3 plus the mass of the boom minus the mass of the counterweight. Okay, and now I'm going to solve for alpha. So alpha is equal to 48 over 7, 1 over mass of the boom, L squared, times this, which is GL over 4, ML times 3, plus MB minus MCW. I can do a little bit of simplification here. Okay, 48 divided by 4 is 12. This L cancels with one of those L's. So that simplifies the overall prefactor so that the overall prefactor looks like 12/7 G over L, and I'm going to move this mass over to here so that all my masses are together. ML times 3 plus MB minus MCW all over the mass of the boom. So this is the angular acceleration that the system would experience if I moved the boom all the way to one end of the crane. Okay, now I'm running out of space here at the bottom, and I'm running out of time, but I can go ahead and plug in all of those numerical values. I know G, that's 9.80 meters per second per second. I know L, that's 24 meters. And I know all of these masses. The mass of the load is 750 kilograms. The mass of the boom, which appears in both these places here, is 1,000 kilograms. And the mass of the counterweight is 2,000 kilograms. This will all look like kilograms over kilograms, so that will end up being dimensionless, just a number. This is going to look like meters per second divided by meters, which will give me radians per second, which indeed are the units of alpha. So if I actually work that out numerically and punch it into my calculator, I get that this should be 0.875 radians per second. Okay, so that's how you do part 2 of the problem. Good luck doing that on your own, and we'll talk again soon.